So during this talk, we will focus on other statistical attacks, which are zero correlation, impossible, and integral attacks. So the different attacks have been introduced by Larstinsen in 97, 98, and by Andrei Bogdanov and its co-author in 2012. The definition we will use for this presentation are as follows. So we call an integral distinguisher a distinguisher where when we have a set of plain text for which the sum of ciphertext is equal to a given value, usually 0. As we will take 0 for this presentation. An impossible differential attack, as you have seen this morning, we will deal with a differential with probability 0. Usually it's a set of differential. And for zero correlation linear attacks, we have a set of linear approximations with correlation 0. And it will also, we will also deal with multidimensional linear attacks, zero correlation linear attacks. To simplify the notation, we will use this short value int, id, and zc to denote integral, impossible differential, and zero correlation linear attacks. The comparison we will do in this presentation focused on type 2 generalized Vestel network. So we define a type 2 generalized Vestel network as such, where the input is divided into B blocks of size C bits. And we have B divided by two nonlinear functions, which takes as input the value of an even branch. And we denote by pi the permutation of the branches. This morning you have seen example of such cipher like Twine and L-block, and also Clefia can be represented as such. We will use a matrix representation of the Ron function, and in particular we will decompose the Ron function into two steps. And we denote by F the matrix representation of the nonlinear layer, and by P the matrix representation of the linear layer. And the Ron function can be matricially represented as a product of these two matrices. A matrix representation of a Ron function is usually useful to find impossible differential, zero correlation, linear approximation, or even integral for a cipher of this type. In particular, we observe that the rules to propagate in the differential context can be described as such, where the orange dot corresponds to a branching operation. And if we observe what happened in the linear context, we can see that the rules of the branching operation in the differential context correspond to the rule which operate on the XOR in the linear context. And conversely, the rule which operate to the XOR in the differential context correspond to the rule we can apply for the branching operation in the linear context. Note that the rule we have in the differential context can also be applied if we want to find an integral distinguisher on the cipher. So from this remark, we define a mirror representation of the Ron function. And in particular, if the Ron function is represented matricially by the matrix R, we represent the mirror representation by a matrix M, and where the role of the branching and the XOR operation are inverted. The matrix M corresponds to the product of the matrix P. The permutation remains the same, and the transpose of the matrix F. Using this mirror representation, we can actually derive zero correlation distinguisher in the same way we were deriving impossible differential distinguisher. meaning that if we have a vector of words representing the input and the output of the distinguisher, we can find such distinguisher by finding an inconsistency in the middle using the matrix R in the impossible differential context, using the mirror matrix M in the zero correlation context, and to find integral distinguisher using the matrix method, we also use the matrix R, but instead of starting from the first round and the last round and trying to find an inconsistency, now we start from the middle, and if we go down forward, we actually will find a first order, usually a first order integral attack, and by going backward, we can find higher order integral attacks. In the impossible and zero correlation context, we can define three type of inconsistencies. In particular, we have been introducing this following definition. We call a distinguisher of type 1 a distinguisher with independent input and output differences. Note that the same definition applied in the zero correlation linear context if instead of differences we take masks. And we denote a distinguisher of type 2, a distinguisher where the input and output differences might be different, should be different. And a distinguisher of type 3 is a distinguisher for which the input and output differences or input and output mask should be equal. So we also notice that these three types of distinguisher apply in the impossible and zero correlation linear context. So in 2014, with my co-author, I show that if there is a relation between the matrix representation of the round function and the matrix representation of the mirror of the round function, then we can deduce that we have an impossible if we have an impossible differential distinguisher, we can find easily a zero correlation linear distinguisher, and the converse is true also. Another relation between zero correlation and integral attack have also been extracted in 2002 by Andre and its co-authors. In particular, for showing such relation, they use the following definition. So they call zero correlation integral distinguisher. It's a kind of particular integral distinguisher for which the output words are balanced. So usually for an integral distinguisher, we want that the output word, the sum of the output word is equal to 0. If the output words are balanced, then their sum, that implies that the sum is equal to 0, but the converse is not true. In particular, they show that zero correlation integral distinguisher implies zero correlation distinguisher with independent input and output mask. That's a zero correlation distinguisher of type 1, as we denoted before. They also show that a zero correlation distinguisher of type 1 imply a zero correlation integral distinguisher, and a fortiori imply an integral distinguisher. And so that's all mostly for any kind of construction. But using this relation, we were able to show that for an alternating type 2 generalized Festen network, we usually have that the number of runs on which a zero correlation distinguisher apply is plus or minus 1, the number of runs an integral distinguisher apply, depending on the type of the distinguisher. If it's a zero correlation distinguisher of type 1, the number of runs on which it apply, it's equal to the number of runs of the integral distinguisher minus 1. If it's type 2, it's usually the number of runs is equal for both zero correlation and integral distinguisher. And if it's of type 3, we have that the zero correlation distinguisher apply on one more runs than the integral distinguisher. And we have similar relation between integral and impossible differential distinguisher. So now that we have compared the search distinguisher, we want to compare the data complexity of the different attacks. For the purpose of this next slide, we denote by beta the false alarm error probability. And when we have M differential involved in the attack, we can show that the data complexity is equal to this formula. In the integral attacks, we can also show that the data complexity is equal to this formula. These formula are just derived what most of the people are using when performing such attack. And so from both formula, it is easy to see that in most of the cases, we have the following relation between the data complexity of an integral attack and impossible differential attack, depending on the type of impossible differential which is we consider. If we want to compare with zero correlation attacks, we have to use an approximation of a quantile of the central normal distribution. So this approximation is a new contribution. And by using this approximation, we can show that the data complexity of zero correlation linear attacks can be computed using this formula. I didn't use any approximation for the quantile phi minus 1 of the success probability. Since in most attacks that we can see in the literature, the success probability is fixed to 85%. Note that for the comparison, we will use the fact that the success probability is equal to 50%. For both integral and impossible differential attack, the success probability is equal to 100%. So using this approximation of the quantile of the normal distribution, we are able to show that the data complexity of an impossible differential attacks is much smaller than the data complexity of a zero correlation attacks if both attacks involve the same number of differential or linear approximations. And if we just fix the success probability of the zero correlation attack to 50%, then we have that the data complexity of the integral attack is larger than the one of the zero correlation attack. But actually, for larger success probability, that's what we use in practice, the data complexity of the integral attack is smaller than the one of the zero correlation attack. So now that we have compared both the kind of distinguishing property and the data complexity of both attacks, we extracted also some relation between the keywords involved in the different key recovery attacks. So first, before showing the results, I want to show you this example. So this corresponds to a key recovery attack on the L-block block cipher. So this cipher was presented this morning during the first presentation. And for this attack, we have a impossible differential distinguisher on 40 rounds, zero correlation distinguisher on 40 rounds, and integral distinguisher on 15 rounds. And actually, we can show that it's easy to switch from the impossible differential distinguisher to the zero correlation distinguisher. And if we assume that the attacks on, if we had one run at the beginning and one run at the end, and we assume that the same key are involved in both the zero correlation and integral and impossible differential attack, then when we do the key recovery, and we had, like here in this example, it's 5 runs before the distinguisher and 4 runs after the distinguisher, then we observe that the keywords involved in the zero correlation attacks correspond to a subset of the keywords involved in the impossible differential attack. Also, if we compare the integral attack, the keyword involved in an integral attack with the one involved in a zero correlation attack only on the last run, because in most of the cases in the integral attacks only a key recovery can only be performed on the last run. Sometimes we can add 1 or 2 runs before, but it's very rare. Then we can see that exactly the same keywords are involved in both attacks. And actually, we observe that using a similar matrix method and using the same matrix representation of the cipher, we can easily find the keyword involved in all of these attacks. To find the keyword involved in zero correlation attack and integral attacks, we use the matrix, the mirror representation of the matrix. But for the impossible differential attack, we use the run function matrix. So I don't know if I will have time to go through this example, but here it's another example where we have a 4-branch Festen network. And actually, if we compute, we can determine what we call sieving keyword. It's in the impossible differential context that corresponds to a keyword for which we discard either key or plain text pair when we perform the attacks. And we also have what we call a guess keyword. It's a keyword for which when we do the attack, no pairs or key are discarded. And so we find such pattern for if we do a key recovery attack on the 3 last run of this cipher in the impossible differential context. We have a 3 sieving keyword and 2 guess keyword. And if we do the same in the impossible differential context, we also find what we will call also a sieving keyword as a parallel to what we have in an impossible differential attack. It's a keyword for which when we perform the attack, we reduce the size of the distribution. And after 2 runs, we also find a second sieving keyword. And in total, for this attack on the last 3 runs, we have 3 sieving keyword and 1 guess keyword. In the integral attacks, for what we have done in our paper, we have actually assumed a small improvement of this attack using partial sum technique, where instead of checking if the value on A1, the sum of the value at this place A1 is equal to 0, we can check, we can use partial sum and check if the sum over A2 here is equal to 0. So, and here I was presenting for the first partial sum, and using the similar method that for the zero correlation attack, we determined that to do the first partial sum, we have to guess 3 sieving keywords. Of course, this relation don't take into account the relation that can exist in practice between the different keywords involved in the attacks, because it will require an analysis of the cascader. And our analysis is more general and work for any kind of type 2 generalized Festen network. So using this matrix representation to analyze the keyword involved in the different attacks, we were able to show that when the distinguishers are strongly related, then the keyword involved in the zero correlation attacks correspond to a subset of the keywords involved in the impossible differential attack. but we notice that the number of sieving keywords is the same, and not only the number of guess keywords change. And for the relation between integral and zero correlation attack, we show that if we only do a key recovery on the last run, and if we don't do the partial sum technique, then we have the same number of keys. But doing a key recovery only on the last run for the zero correlation attack, it's much more demanding than doing a key recovery on the first and on the last runs. And in particular, we managed to show that in general, because we can invert in the first and in the last runs, we have that the number of keywords involved in an integral attacks is larger than the number of keywords involved in the zero correlation attacks. So to resume, in this paper we have compared impossible differential, zero correlation, and integral attacks on type 2 generalized Feistel network. We actually have been able to show a strong correlation between the keyword involved in the different attacks. And we have also observed that a similar analysis can be generalized to other constructions.
Thank you, Celine. Are there any questions? Yeah, I do have a question. So if so now you're operating under the assumption that the f function, in this type 2 Feistel is bijective.
Yes.
So what can you say about the equivalences or inequivalences if you replace it, say, by a balanced function?
They don't work in the same way. I guess the matrix representation and the rules that we are using to propagate should be analyzed with more care.
Let's thank Celine and all the speakers of this session again.